So a little review of simple linear regression. Then we'll move to multivariate linear regression, where you have more than one predictor variable. And then we'll start to pivot to using multivariate linear regression to answer causal questions. But before we do that, there will be an interlude about just what is a causal question exactly, kind of making that a little more formal. And then talking about how to use multivariate linear regression to do something called standardization so that you could estimate causal effects. So first, let's start with a review of simple linear regression models. So a simple linear regression model is a model of the distribution of y given x. And it has three parameters, B0, B1, and sigma. And for any given big values for those three parameters, define a different distribution of y given x. So B0 and B1 define a line, together the intercept and the slope of a line. And here's one particular line with intercept 10 and slope 2. And everyone remembers from high school, y equals mx plus b, right? That's what this is, right? So these two parameters define the line in simple linear regression. And the simple linear regression model says that the expected value of y given x is equal to the point on the line corresponding to that value of x. So the expected value of y given x equals 5 here, according to this model, is the point on the blue line, about 20, where x equals 5. And then the other component of the linear regression model says that the actual y values are equal to this line plus noise, or plus a random error, which follows a normal distribution. So y given x is normally distributed with mean equal to b0 plus b1x and standard deviation sigma. And so when you do a linear regression, you just look at the data, which are the black points in this picture, all the black dots, and you try to find the parameter values b0 and b1, which define the line, which kind of best fits these points under the assumption that these points are all normally distributed about the line. And so like at any point on the line, if you had x at that point, you would generate the y by adding random noise to the line. Here's one example that we did where we had cancer death rate as the outcome and poverty, percentage of people in poverty as the predictor variable. And each dot is a county. So each unit is a county. And we found the best fitting line to this data, assuming that it follows a simple linear model, was that the expected cancer rate, given that the poverty rate was equal to x, is 147.3 plus 1.9 times the poverty rate. And the interpretation of this is that if you compare two counties and one county has poverty rate that's 1% higher than the other, you'd expect, in expectation, on average, the county with the higher poverty rate will have 1.9 per 100,000 more cancer deaths. And this is a descriptive regression or a predictive regression. Like you can use this to kind of describe the association between poverty percentage and cancer death rate across counties. And it's not saying anything causal necessarily. Okay, here's another example where the treatment variable was binary. This was data from a randomized trial. The predictor variable was just an indicator for whether each subject received treatment or not. And the regression then tells you the expected value of the outcome under each level of the predictor. And there are just two levels, so there are two expectations, and you can always draw a line between 2 points. So here's the regression line. And in this simple example, again, the interpretation of the slope is that if you compare someone who received Sulindac to somebody who didn't receive Sulindac, in expectation, the difference between the number of polyps they'd have at 12 months is equal to the slope of the line, which is just the difference in the averages under treatment and no treatment. And because this is an RCT, you can actually interpret this causally, but we'll talk about that more later. But it also has that same interpretation as just a comparison across levels between units with different levels of the predictor variable. So here's an extra topic that we didn't talk about. We've talked a lot about interpreting the slope of the line as the association between the predictor variable and the outcome, but we hadn't really talked a lot about the intercept. The book that we often use for this class, Regression and Other Stories, talks about this in section 10.4. So you can center a predictor variable to make it more interpretable, and I'll explain what that means. So they give an example of a regression of adult weights in pounds on heights in inches. So the expected weight given height equals negative 172.9 plus 4.9 times height. So that means if you compare two people, one of whom is 1 inch taller than the other, their expected difference in weight is about 4.9 pounds. So that's the interpretation of 4.9 in this regression. The interpretation of negative 172.9 is that the predicted weight for a 0 inch tall person is negative 172.9 pounds. So this is total nonsense, right? That's not really an interpretation at all. So if you want your intercept to be more interpretable so that it doesn't correspond to a value of the predictor variable that's impossible or completely out of the range of your data, you can use a centered predictor variable. So you can define centered height as height minus 66 inches, since the mean height is about 66 inches. So then if you do a regression of weight on centered height, that yields that the expected value of weight given observed centered height is equal to 153.4 plus 4.9 times centered height. So the slope stays the same. You know, the comparison between two people who differ in height by 1 inch still has the same expected difference as it should. But now the intercept has the interpretation of the expected weight if your centered height is 0, which means you're exactly the average height. So often, for the sake of interpretability of regression coefficients, you might want to center the predictor variable before fitting the regression. Okay, here's a tweet I came across. Someone tweeted another day without using y equals mx plus b, as they told you that would be important in school, but it wasn't. Type of spirit went viral. Korean Carr, who's this statistics PhD student at Harvard. Hard to pick a worse example of useless math. Statistics, AI, computer graphics optimization, the concept of it is everywhere. If you rely on products that require people to collect data and compute a trend, then you've relied on this math. You just might not know it. So now you guys all know it, right? Powerful formula. All right. Okay, so now let's move from y equals mx plus b to having more than one predictor. It's a pretty simple jump conceptually, I would say. So in the simple linear regression model, you just have an intercept and you have a slope for your one predictor. In the multivariate, you have a bunch of predictors. You have little p predictors. And you have that the expected value of the outcome, given that all of those predictors take certain values, is just equal to an intercept parameter again, plus coefficients for all of the different covariates or predictors times those predictors. So what does this look like? Before you had a line, like you had x and on the x-axis, y on the y-axis, and you had a line. Here now you have like x1 and x2. And here's y, and it looks like a plane. If you have equations that look like this, so this is the expected value of y given a value of x1 and a value of x2. Okay, here's an example from Regression and Other Stories. It's a little cringy, I guess, because it's about IQ scores, which I just find a little cringy, but they can be an important measure. I don't know if you want to do a study of lead poisoning or something, it can be an important outcome variable. So here, the example that they give is trying to predict or find associations between a child's IQ test score and certain facts about the child's mother. So the two variables related to the child's mother are whether they completed high school and what their IQ score is. So the first one is a binary variable, and you can fit a linear regression to a binary variable, as we've seen. Here's the simple linear regression, just looking at the relationship between whether the mother completed high school and the child's test score. And so the interpretation is that if you compare two kids, one whose mother completed high school and the other who didn't, in expectation, the one with the mother who completed high school would score 12 points higher on the test. And then Here, the interpretation is if you compare two kids, one whose mother has a 1 point higher IQ, you'd expect the kid with the mother with a 1 point higher IQ on average to have 0.6 higher IQ than the other kid. Now, you can also do a multivariate linear regression where you regress the kid's score on both mom high school and mom IQ. And the result here is that the expected kid's score, given these facts about the kid's mom, is 26 plus 6 times what the indicator plus 6 if the mom attended high school, plus 0.6 times the mom's IQ, plus random noise. So the coefficient of the maternal high school completion variable is comparing children whose mothers have the same IQ, but who differed in whether they completed high school. The model predicts an expected difference of 6 in their test scores. It's a comparison between, units, in this case, children, who have the same other covariates, but who differ on the covariate of interest, right? It's how much you expect them to differ by on average. So similarly, the coefficient of maternal IQ has the interpretation that if you compare children whose mothers had the same value of mom HS, who's of the same maternal high school completion variable, but whose mothers differ by 1 point in IQ, then you'd expect to see a difference of 0.6 points in the child's test score. I think I might have messed this up because I don't think this was supposed to be the same. Anyway, hopefully it still works. In general, you'll have different coefficients though when you do multivariate compared to simple linear. Another thing that you can add in a multivariate regression model is interactions, where you can allow the slope of one covariate to vary depending on the value of the other covariate. So in this case, you can allow the slope of mother IQ score to vary depending on maternal high school completion. So you can say that here in this plot, the dark dots are kids whose mothers did not complete high school, and the light dots are kids whose mothers did complete high school. And you can see that the slopes of the predicted regression lines in these two cases are different. So the way you allow for that and model that is to say the expected value of kid IQ given mom IQ and mom high school. You say that it's equal to a linear function of mom high school plus mom IQ, and then mom high school times mom IQ. That's how you include an interaction and allow the slope of mom IQ to vary depending on mom high school. So here are the coefficients. The expected value of kid IQ given these variables in a model with an interaction is -11 plus 51 times mom high school plus 1.1 times mom IQ minus 0.5 times mom high school times mom IQ. So if mom high school is 0, this reduces to just -11 plus 1.1 times mom IQ, because this 51 times mom high school is 0, and then this interaction is 0, right? If mom high school equals 1, so if the kid's mom did go to high school, then this turns into -11 plus 1 times 51, so that's 40, plus 1.1 times mom IQ minus 0.5 times mom IQ, so plus 0.6 times mom IQ. So the slope or the dependence of the outcome on mom IQ varies depending on whether the mom went to high school or didn't. You don't have to. I mean, yeah, you could just start from positing the more complicated model, but it is, I think, good practice if you're developing a model to build up, to start with the simplest models and see what they look like and keep adding things, making them more complicated. If the mom went to high school, so two kids whose moms both went to high school, but who differ by 1 in mom IQ would be expected to differ in their IQs by 0.6. Like the individual coefficients don't have as much interpretability if you're fitting a model with an interaction, but for each given value of the variable that you're less interested in. So in this case, mom high school, you can see what the coefficient of the variable that you're interested in interpreting is. So yeah, it requires like another step to get to the ability to phrase the output in terms of comparisons between people who have the other variables the same, but are different on kind of the variable of interest. Remember, I showed you like response surfaces for the form of multivariate linear regression where you don't have interactions, where it's just like something times x1 plus something times x2. So if you include interactions, they can get really curvy. And you could also include things like not just x1 times x2, but even if you just have x, you can have x and x squared. And you can have a curvy line like this. And this is also a linear model. These are all linear models, even though they don't look like lines anymore. And that's because the term linear might be slightly misleading. Multivariate linear models, they're linear in the coefficients. So like in the betas and the parameters, they can be very flexible functions of the x's. So anything that you can write in this form of beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, where here, let's say x3 is equal to x1 times x2. That's a linear model, even though really you only had x1 and x2, and you created this x3. So now you have this linear model is actually a flexible function of your two original variables. Or in this case, you originally only had x1, let's say, and you created an x2, which is x squared. And now you have a flexible function of x1, and it's still a linear model, a multivariate linear model. So by adding a bunch of interactions and a bunch of like powers of your variables or whatever you want to do, you could get arbitrarily like flexible linear models that don't put a whole lot of restriction on what the shape of the relationship between the x's and y is. We'll talk about this later, but just something to keep in mind. If you have enough data, there's no reason typically to not include interactions, or I hope this isn't too general a statement, and it's being recorded, unfortunately, so I can't ever deny that I made it. But yeah, I think if you have enough data, there's almost never a reason not to fit like a really flexible model. But if you don't have that much data and interactions aren't that important, if you add them in, it could make your estimates high variance. We'll talk later about model selection and how to land on a good choice for what model to choose. We're not going to talk about that today, but it's a good point that it's something to consider, right? And the trade-off is between bias and variance. You'll always get closer to the true model the more complicated a model you have. That can't make you wrong, because the simpler models are like special cases of the complicated ones where just certain coefficients are equal to 0. But it can make you lose certainty in your estimates unnecessarily if really the interactions are really weak or aren't there. So here's a big blurb of text from the textbook that I just want to take some time to read, and we'll dwell on this for a little. It's on page 134 of Regression and Other Stories. It's about how to interpret regression coefficients in a multivariate model. And it's repeating a little bit of what we've said, but it's worth just going over again because interpreting these coefficients is important. So they say that there are basically two ways to interpret regression coefficients. One is the predictive interpretation, or I would say also descriptive interpretation could be another way to put it, where you consider how the outcome variable differs on average when comparing two groups of items that differ by 1 in the relevant predictor while being identical in all the other predictors, right? Under the linear model, the coefficient is the expected difference in y between these two items. And this is the sort of interpretation we have described so far. Then the counterfactual interpretation is expressed in terms of changes within individuals rather than comparisons between individuals. So here, the coefficient is the expected change in y caused by adding 1 to the relevant predictor, while leaving all the other predictors in the model unchanged. And this is the type of interpretation that arises in causal inference. Okay, so we'll skip this paragraph, but typically when causal language is not warranted, the most careful interpretation of regression coefficients is in terms of comparison, so the descriptive or predictive interpretation. For example, when comparing two children whose mothers have the same level of education, the child whose mother is X IQ points higher is predicted to have a test score that is 6X higher on average. Or in more general terms, comparing two items, I and J, that differ by an amount, X on predictor K, but are identical on all other predictors, the predicted difference, yi minus yj, is the coefficient for variable k times that difference x on average. So the next sentences here are key. This is an awkward way to put things, which helps explain why people often prefer the simpler formulations, but those can be misleading. And this is also kind of key. You just have to accept that regression, while a powerful data analytic tool, can be difficult to interpret. So I think in the examples we've given so far, the interpretation is a little bit weird, and it's not clear why you'd want to be making these comparisons exactly when you're under that descriptive framework, which hopefully makes you want to turn to the counterfactual interpretation where things are nice and easy and interpretable and meaningful. So that's what we're going to do next. Talk about when and how you can use multivariate linear regression to estimate causal effects. Causal inference fundamentals. So I have two clips from The Simpsons that illustrate some typical attitudes towards causality. The first illustrates association is not causation, which is true usually, and is a trope that I think most people are familiar with, or some wisdom that most people I think are familiar with. But sometimes it actually is, right? We estimate causal effects by looking at associations. They might be special kinds of associations or associations in special circumstances. And causal inference might be, you might say it's the study of formalizing when association is causation and like what associations are of causal effects. To formalize causal effects, we'll use this terminology of potential outcomes, okay? So a potential outcome is a value of an outcome that you would observe under a certain treatment assignment. So let's say Winston has a headache. He could either take aspirin or take nothing. And half an hour later, let's say if he takes nothing, we'll call that A equals 0. His potential outcome, Y, if he were to take treatment 0, we'll use this notation, is equal to 0, which means he still has his headache. If he were to take aspirin, his potential outcome is 1. So there's this kind of idea of everyone has a property of themselves, what would happen to them under each treatment assignment, regardless of what treatment they actually take. So for Winston, the causal effect of aspirin is Y1 minus Y0. It's the difference in the outcomes under the two different treatment assignments, like what the outcome would be for him, and it's 1. Okay, so there could be, with a binary outcome and a binary treatment, 4 types of subject, right, or dog. So there's the people who the treatment would help, where they'd still have a headache if they don't take aspirin, but they don't have a headache if they do. There's people where the drug has no effect and they still have a headache either way. You could also have no effect because you'd get better either way, even without treatment. Or treatment could actually be harmful, right? So causal inference is usually about trying to estimate population level causal effects. So let's say the top left in each grid of dogs is like the same dog. It's their potential outcome under no treatment and their potential outcome under treatment. So the top one, treatment helps them. The middle one, it does nothing because they get better either way. So a population level causal effect looks at the average of what the outcome would be if everyone in the population took no treatment. So here it's 1/3 because 1/3 of the population would get better even without treatment. And here it's 2/3 with treatment. And the average causal effect is the difference between the average potential outcomes under treatment and no treatment. So it's 2/3 minus 1/3. So it's 1/3. Now, the fundamental problem of causal inference, this has been dubbed the fundamental problem of causal inference, is that, of course, for any given unit, you don't get to observe both their potential outcomes. You only get to observe the outcome corresponding to the treatment that they actually took. So now you want to know the average in the population of what the outcome would be had under no treatment, but you only get to observe the outcomes of these dogs who didn't take treatment. And here you only get to see the dogs who did take treatment. So you don't know what any of these expectations are. If you just naively compared the outcomes in those who weren't treated to those who were treated, then your comparison might be biased by what's called confounding. So that's if there's a common cause of treatment and the outcome, which makes it such that people taking one treatment are systematically different from people taking the other treatment in ways that impact the outcome. So that when you compare the treated to the untreated, when you compare their outcomes, the difference is not due to treatment. It's due to the thing that's causing some to be treated and others not to. So, for example, let's say this other variable L is initial headache severity, and worse headaches make you more likely to take medication. So there's this causal arrow from L into A. It influences treatment decisions. And also worse headaches are more likely to still be around in half an hour. So then those who take treatment would disproportionately have worse headaches. And it might even look like treatment causes headaches to not be around because it's just those who are worse off to start with who are the ones taking treatment. If you just do a naive comparison between those who are treated and those who are untreated. One solution, like the kind of gold standard solution to the problem of confounding, is randomization. So if you randomize people to take treatment or not, like you flip a coin and it's up to chance, then that breaks the connection between the confounder and treatment, because nothing influences whether you take treatment except for the outcome of the coin flip, the randomization, right? So you no longer have a common cause of treatment and the outcome. So there are no systematic differences between treated and untreated units, except those differences that are actually due to treatment if you randomize. For those who are interested, it's okay if you don't follow this. In math, you'd have that the potential outcomes under randomization are independent of treatment. So what would happen to you under each treatment is independent of what treatment you actually receive if your treatment's randomized, because all that influenced your treatment was this coin flip. So how could it be related to anything that was determined before treatment? So that means that the average of the potential outcome under, let's say, treatment little a, let's say under treatment, is equal to the expectation of the potential outcome given that treatment equals some value, because they're independent. So if you see that a certain treatment was given, that has absolutely no bearing on this expectation. So the overall expectation is just equal to the conditional expectation. That's what independence gets you. And in people who actually received treatment little a, their potential outcome under treatment little a just is their observed outcome. So this is equal to the conditional expectation of the outcome given that they received treatment. And this is just something that you can estimate with a regression, right? We're at a conditional expectation of your outcome variable given a covariate, and everything's observed. We don't have any potential outcomes that we can't see anymore. So now we're at the point where we could use our regression method, as in that example with the randomized trial with the polyps, to estimate the effect of treatment on the outcome. This is for people who are interested in a little bit more rigorous explanation of causal inference, and probably you're going to cover this in your epi classes also, but it's not critical to follow this. Okay, so what do you do if you don't have randomization, right? If you can't do a trial because it's too expensive, or it would take too long, or it's unethical to randomize people to treatment in a certain scenario, what do you do? Suppose we have observational data, and we're lucky that we get to, or through careful planning, we collected data such that we got to observe all of the inputs to the treatment decision that are also associated with the outcome. So here, L, let's say, represents everything that the doctor thinks about when they decide whether or not to give you treatment A. That's also associated with the outcome. There can be unobserved variables, U, which you didn't collect, which might be like a common cause of these inputs to the treatment decision and the outcome, but they're not direct causes of the treatment decision. They're not direct inputs. So if you observe all the direct inputs of a treatment decision that are also associated with the outcome, either by causing it or just being associated with it through some other common cause, then within levels of this variable, so like for a given value of these confounding variables, it's as if nature is running a randomized trial. So within levels or for a given value of the covariates which influence treatment and are associated with outcome, a naive comparison of the treated to the untreated gives you the causal effect within that group. It gives you the effect of treatment in that group. Just like in an RCT, association is causation. Within levels of the confounders, for those who are interested in like a slightly more rigorous, take, I think you'll get this in epi. This is called the ignorability or exchangeability assumption. And like the key thing about it is that, so before, remember with a randomized trial, the potential outcomes were just independent of treatment. Now the potential outcomes are conditionally independent of treatment given the covariates, so that the expected value of Y of the potential outcome YA given the treatment value received and the covariates is just equal to the conditional expectation given the covariates alone. Like the treatment received adds no extra information about what the potential outcome is. And there are some scenarios other than this graph where exchangeability could hold, and so that therefore you could estimate causal effects. But maybe this graph is maybe the most plausible like scenario that you might be able to approximate in epi, because you could always ask doctors, for example, what do you take into account when you decide what treatments to give and collect those variables? Whereas it's harder, for example, to figure out what all the inputs to an outcome might be and measure them. So for example, let's say it's the question of interest is like when to start an HIV medication. Doctors might look at CD4 count and RNA levels, right? And so you can measure those, and that might be just about all they look at, in addition to age and maybe a few other things. So you can reasonably approximate this situation to try to look at the effect of starting early. Okay. So here the treatment is like when you give antiretroviral therapy, and CD4 count is the confounder because it's what influences the decision of when to give antiretroviral therapy. And what we would have is that two people with the same CD4 count but different treatments, the expected difference in their outcomes can have a causal interpretation. And maybe hearing this language is starting to draw some parallels back to the multivariate linear regression case and how we can use multivariate linear regression to estimate causal effects. It's the coefficient of treatment in the regression that also includes L that will have a causal interpretation. U is an unobserved variable, so it doesn't enter into our calculations at all because we don't measure it. It's an unmeasured variable. The only reason I included it here is just to show that there are allowed to be unmeasured common causes of the covariates that aren't treatment and the outcome, but there can't be any unmeasured direct common causes of treatment and the outcome. A is the treatment of interest, L is a confounder that's observed, and Y is the outcome. So the key thing is that in this scenario, you can observe all the inputs to the treatment decision A that are also associated with the outcome. So here L is associated with the outcome because it's a cause of it, but also because there's an unobserved common cause of L in the outcome. And in either of those scenarios, L would be a confounder, right? If it influences A and it's associated with Y, either because there's a common cause or because it directly causes Y itself. When you hold L constant, you're essentially blocking the path from U into A that goes through L and making it not confound you anymore. Yeah, and you'll, in your epi classes, you'll learn all about how to like encode the assumptions that you need to estimate a causal effect using graphs like this. But yeah, so this is like a common situation that you should look to see if you can approximate and see that you're in before you start trying to estimate the effect of A on Y. But now let's say you think you're in this situation. On an intuitive level, the meaning is that you have ignorability or exchangeability if within levels of your confounder, so like for a given value of your confounder, it's as if there's an RCT being run, as if nature is running an RCT. I'll say it a few different ways. That's one way. Another way to think of it is that this graph describing the relationships between the different variables holds. So if all the direct inputs into the treatment decision A are measured, so like here L is measured, or all the direct inputs that are associated with Y in any way are measured, then exchangeability or ignorability holds. So that's another way to put it. And then the most technical way to put it is that if ignorability or exchangeability holds, then the potential outcomes are independent of the actual treatment given, conditional on the confounders, on the observed covariates, L. Let's say we're in this situation. We think that this causal graph, it's called the causal graph, describes the process that generated our data where we have LAY. That's our data, the confounders, the treatment, and the outcome. So now how do we actually estimate the effect of the treatment A on the outcome Y? So I said we have within levels of the covariate, let's say it's just binary. In that example we were giving before, it could be severe headache or not severe headache. That's the confounder. So it could be 1 or it could be 0. Restricting our attention to patients, subjects, dogs who have L equals 1, the conditional average treatment effect or the treatment effect in that group, let's just say it's negative 0.25. And you could get that just by doing a naive comparison because it's an RCT, right? Within that level of L, you could just compare the mean outcome in those who took treatment and those who didn't and take the difference. So it cures a quarter of the people is what this means. 1/4 fewer people will have headaches with aspirin in the severe headache group. And then the treatment effect isn't necessarily the same in all groups, right? So let's say in people with mild headaches in the L equals 0 group, the average effect is 0. So aspirin does nothing for mild headaches, let's say, but it does cure a decent proportion of severe headaches. So then what's the average effect of aspirin? It's the effect in the L equals 1 group, right, which is negative 0.25, times the probability that L equals 1. Like you have to weight the effect in each level of the confounders by how prevalent that level of the confounders is. So it's the average effect in the group with L equals 1 times the probability that L equals 1, plus the average effect in the group with L equals 0 times the probability that L equals 0. So that's negative 0.25 times 0.5 plus 0 times 0.5. So the average effect in the whole population then is negative 0.125. Okay, so that's like a simple example of this with one binary predictor that didn't really use like regression at all. We did compute some conditional expectations and differences, and we know that we can do that with regression. So how does this work with regression? We want to know the average, that's what E means, expected value. We want to know the average of the potential outcome under, let's say, little a is, let's say, no treatment. So this is what we did before in our simple example. You can sum over all the values of the confounder, little l, and this is equal to the mean of the potential outcome given that value of the confounder times the probability or prevalence of that value of the confounder. It's like the weighted average of the potential outcome. But we still can observe potential outcomes. So this doesn't help us yet to express it like this. So now the next thing we do is we use the ignorability or exchangeability assumption that this conditional expectation doesn't depend on A. So we can just throw it in, we can just condition on it and it doesn't change. It's the same, right? Knowing what treatment you got tells you nothing about your potential outcome once you're conditioning on the covariates. So we can just throw that into our regression too, and it tells us nothing. We're allowed to do that. But then we do this trick that if your observed value was A, then the potential outcome, had you received A, well, that's just what your outcome was. So now we have this expression down here, which is like the standardization formula or the G formula, which says that the mean of the potential outcome is equal to the sum over values of the covariates of the expected value of Y, the observed outcome, given the covariates and the treatment, times the probability that the covariates are equal to that value. So it's the sum over value of the covariates of the conditional expectation of the outcome, given that the covariates equal that value and that treatment is equal to the treatment level of interest, times the probability that the covariates are equal to that value. When we have a conditional expectation, think regression, right? Regression tells you what this is equal to. So what we need is a regression for the outcome given the confounders and given the treatment. So we can do that with a regression model, and then we can sum over all of the values of treatment that conditional expectation times the probability that treatment takes those values. And a simple way to do this that works even if like the confounders are continuous is to just take everyone in your sample and take their expected outcome given whatever their covariates actually were and given the treatment of interest, and just take the average of that. And that's called the G formula. That's how you would estimate like a counterfactual, or that's how you would estimate the average outcome in a population under treatment had everyone taken treatment little a, just from observing LA and Y, assuming that this graph holds. So the average automatically weights by this probability. Let's say there are 10 people with L equals 1 and 10 with L equals 0. If you just take this average, it'll just weight them equally, right? Which is what it should do. Let's say it's 10 with L equals 1 and 5 with L equals 0. It'll weight the L equals 1s twice as much as the L equals 0s because there are twice as many of them. And it'll do that automatically. And then what's nice about this is that it will also work even if you have a continuous L, where you couldn't just compute that probability simply. So anyway, this was a rigorous derivation. Don't worry if you got lost in this part. I keep saying that because I know that we have some like PhD students in the class, some epi PhD students, and we also have master's students. And I think for the PhD students, it's good to be exposed to this, and also for master's students who are interested, but also don't worry about it if you're not following the derivation. I just want to go over again the key points. The key points are that if you want to estimate the effect of A on Y, if you have a treatment and you want to estimate the effect of the treatment on an outcome, you need to observe all the inputs to the treatment decision that are also associated with the outcome. And then you fit a regression for the outcome given the treatment and the covariates, right? You fit a regression model. And then you just take the average of the predictions from that model over everyone in your data set, pretending that they received like the treatment that you care about, treatment 1, let's say, if you want to know what happened had everyone been treated. And then if you want to know what would happen had everyone not been treated, you do it again with A equals 0, and you take the difference. And there's your average effect estimate through standardization. So let's say, for now, we want to know what would have happened, like what would the average outcome be in the population had everyone taken treatment? That's what we're interested in. Then you would set everyone's treatment value equal to 1 in your data set and output the predictions from your model. And that's step 2. And then step 3 is to just take the average of all of those. Here, I just combined those 2 steps into one. So you could also just call it a 2-step process.